So the topic is going to be the electron shells and the binding energies, in which we will be revising a few things about the electron shells which we have already gone through, and then we will be adding some new concepts about the binding energy and electron shell energies. So starting with the electron shells, the nucleus, which is the central part, which is in green, is going to contain the nucleons, which are neutron and protons, and around these are going to be the shells, which are going to contain the electrons. So the innermost, this one is going to be K, then L, then M. What we know so far is that K shell, by using this formula 2n square, K shell can contain maximum of 2 electrons, whereas the L shell can contain 8 and M shell can contain 18 electrons. And the first shell which is going to be filled is going to be the K, then L, then M, and in this way the electron shells will be filled depending on the number of electrons that element is supposed to contain. Now, one other thing which is important is that all shells except K shell contain more than one subshell. So you can see in this example that the K shell is containing one shell, no subshell, whereas the L is going to show you 2 subshells. So electrons are arranged in 2 subshells in the L shell in this case, and so it would be in M. So this image we will be using to explain the forces which are acting on the electrons. So you know that the central nucleus is positively charged and the electrons are basically negatively charged. So there is an electrostatic force, which is a force of attraction between the positive and the negative charge, and this force is acting on all the electrons which are rotating in the shells. So the closer the electron is to the nucleus, the more electrostatic force is going to be acting upon that particular electrons. So for example, this electron will experience the most electrostatic force, and then as it is, this electrostatic force is known as potential energy because it is due to the position of the electron, and then the electron is revolving and rotating in the shell itself, say for example in this direction. So it is also having some kinetic energy due to the movement, but issue is that the potential energy, which is due to the electrostatic force, is always larger than the kinetic energy. So this results in a net negative force experienced by the electron in any shell, and that net negative force is basically the actual energy of the bound electron or that specific electron. So this is a graph which is showing us the net or actual energies of the electrons depending on the shell of the electron, and in this one we are going to use an example of an aluminium, and in this case the net energy or the actual energy experienced by an electron in a K shell is going to be minus 1.56 kilo electron volt. Remember, as it's a negative energy, because the potential energy is larger than the kinetic energy, so the net actual energy is going to be in minus value, and this is in case of aluminium and K shell of aluminium, the electron is going to experience minus 1.56 kilo electron volt, and as the electrons fill from K's outwards, so the first electrons in the K are going to experience 1.56, and then as we move to the L shell, the net negative energy experienced by the electron in the L shell is going to be minus 0.08 kilo electron volt. Now there are one important concept here, and that is that which of this energy is greater. So you remember that as these all energies are in negative value, the less negative value is going to be a greater value. So actual energy of the electron in L shell, which is minus 0.08 kilo electron volt, is greater than the energy experienced by the K shell, which is minus 1.56 kilo electron volt. So the larger value is this one, as it is closer to zero. So remember that the outermost shell has maximum energy, which is the least negative value. So this is a common MCQ which is asked. But remember, if it is the actual energy or the net energy of electron, the outermost shell is going to show you the maximum energy. Now we come to the definition of binding energy, which is different from the actual energy of the electron. Now we know that this is the energy which is a negative 1.56. So to make it zero, that the electron should experience no net attraction by the nucleus, you have to give plus 1.56 keV to make it a zero. So this energy which you need to give to the electron to make it a free electron and get it out of the binding force of the nucleus is known as the binding energy for that shell or for that electron. And these energies, the binding energies, are always positive value, whereas the actual energies or the net energies of an electrons are going to be the net negative values. So just converting the shell or electron energy, which is negative, to positive value is going to give you the binding energy for that particular electron or electron shell. So just to summarize the things which we have discussed, there is going to be a bound electron, which is due to the electrostatic force which is between the nucleus and the electron, which gives a negative potential energy. The kinetic energy which is gained by the electron as it rotates, but it is less than the potential energy. So total energy is the negative. So the real and actual energy of an electron in a bound state is going to be always a negative energy. So this negative energy, whatever it is, you need to give that energy to the electron to free it, which is then known as the binding energy. And binding energy is a positive magnitude of real energy, and depending on the higher atomic number, you will need a higher binding energy, or say for example you have more protons in the. So as the number of protons are going to increase in the nucleus, they are going to cause an increased proton positive charge, which is going to create more potential energy for the electron in the negative charge state, which will then result in a more negative energy of that electron. So you will then need more binding energy. For example, if it's say 40 keV in negative, so you will be then requiring positive 40 keV to remove that particular electrons out of shell. And both actual and binding energy are expressed in kilo electron volts. So this is a last image which is showing the energy level diagram for the tungsten. The tungsten will be using again and again, so to make sure you have an understanding of tungsten now, the K shell in this case is going to show you a actual energy of an electron of minus 70 keV, and this is the electron and net and negative electron energy in the K shell. And in L shell it is going to show you a minus 12 keV and in M shell it's going to show you a net negative energy of -2 keV. So now if I want to calculate the binding energy or the energy which I need to give an electron in a K shell to release it from the force of the net potential attractive force of the nucleus, I will now need to give positive 70 keV to release it, and if the electron needs to be released from L shell, it would be plus 12, and if it's in the M shell, say it's plus 2. So this makes an understanding of the tungsten electrons revolving in the tungsten, how much energies would you require to get them released from the nucleus power.